Could you tell me what is mean by CSMA?
It's like a protocol to when two node to when the bus is free, when the two nodes want to transmit the message simultaneously, this protocol will help to choose the winner who want to transmit to avoid the collision.
Can you repeat?
Actually, when the bus is free, when the two nodes are trying to communicate a message, start a message, the CSMA protocol will help to avoid the collision and choose the winner based on the identifiers.
CSMA is not for choosing the winner actually. CSMA is something like it allows more than one node to try to access the bus when the bus is free. Let me tell you another example. In a library, we have a book which deals about CAN. What the librarian says, whoever come at 7 a.m. will get the CAN book. This is like CSMA. This is like a rule, like whoever come at 7 a.m. will get the book. But at the 7 a.m., two people have come. Both of them want the same CAN book. They don't want different book. Both of them want same. As per the rule told by the librarian, whoever comes at 7 can get the book. But we have only one book. What will we do now? We have to give any one. What is the mechanism? Whoever come at 7 will get the book. That is called as CSMA. That means they monitor the library. The moment it becomes 7, they are coming to the library. That is called as they are sensing whether the time is 7. The moment they come to 7, they come for the book. Both of them are come. But unfortunately, we have two people at that point. To judge the winner, we have to use another mechanism that is called arbitration. The route that they are seeing, when the bus is free, whatever the node that we have in the bus can try to run. That is called as carrier sense multiple access. In order to transmit that, every node used to send whether the bus is free, bus is free, bus is free. How they will come to know? How they will come to know the bus is free? Let me explain you via a diagram. We have, see, this is our canvas. It used to be terminated with 120 ohm resistor. See, these are three issues that I have. when you measure the voltage between these two lines, you will get threshold voltage. 2.5 volt will be the threshold in CAN. When you measure the voltage of the bus and you are getting 2.5 volt, means the bus is free. You have a 0 as reference line, and then you have 2.5. When you have every node sees the voltage level, when they see 2.5 volt for a time, for a period of seconds or milliseconds, they are able to see 2.5 volt. If that is the case, bus is free. Usually during the transmission of data, this 2.5 volt will change. Actually, it used to fluctuate between some 3.2 volt or something like that, 1.5 volt. There will be variation in the voltage. If there is variation in the bus voltage, they will come to know that, okay, some transmission is going on in the bus. We should not do anything. We have to keep quiet, because if some transmission happens, no other node has right to transmit anything. If there is already a transmission in the bus, how they come to know that? There should be a fluctuation of voltage in the bus. When you measure the bus voltage, you should see a fluctuation. If there is a fluctuation, okay, there is some communication is going on. If there is no fluctuation and you are always able to get 2.5 volt, then that is called as bus free. The moment they come to know the bus is free, assume this node has some 3 messages, like zero x 30, 0x45, 0x 98. Usually the message IDs will be given in X. That's why I have given that. $225, 0x 345, 0x 12. See, usually in automotive ECUs, they used to maintain something called as transmit queue. That means each message that they want to transmit, they will arrange them in a queue. We are going grocery shop. If there is a heavy crowd, they will keep us to stand one after another. Similar to that, when I ECU want to transmit a message, it will organize them one after another. Every ECU used to have. When the bus is not free, they will simply arrange them in the queue and then they will wait for bus free. How they will come to know the bus is free? When there is constant voltage of 2.5, when they are able to see 2.5 volt threshold voltage, they will come to know, okay, it's time for us to transmit. How they will try to transmit? Everybody will send the startup frame. When each one of them have a queue, they won't transmit. Each issues has a queue, 30, 45, 98, and then each one of them has three messages as per this diagram. So will they transmit all the 3 messages in one go? The answer is no. It is not possible to transmit all the 3 messages in one go. Everything should go serially. If that is the case, the bus is free. Every node has a right to transmit. They will transmit the message from the top of their queue. In this one, you assume this is the top of the queue, so whatever the left side. The 30 is the top of the queue in ECU 1. And then in ECU 2, it is 225. In ECU 3, it is 67. See, every ECU has a list of message to transmit, but the bus is not free. They are arranging them in a queue and they are waiting for the bus free. The moment they come to free, as we have 3 ECUs here, everybody will rush. All 3 ECUs will rush for the bus. What they will try to transmit? The ECU 1 will transmit the 30. ECU 2 will transmit the 255. ECU 3 will transmit 67. As per the common rule that we have in CAN, everybody has a right to transmit when the bus is free. So now 3 peoples are there for the bus, 30, 225 and 67. Who will win the bus? Now there should be another mechanism. That mechanism is called as arbitration. Like whoever has the least identifier for their packet. As per 30, 225 and 67, the 30 is very least number. So he will win the bus and he will complete the transmission first. And then 67 will do because that is the next least number. Then 225. Once these 3 packet transmission is completed, next batch will come. The 45 will come to the top and then 345 will come here and 64 will come here. Again, the arbitration will happen between 45, 345 and 64. As per that logic, 45, the ECU 1 again, the 45 will go fast and then 64, then 345. After this batch is over, we get the third batch, 98, 10 and 12. In that case, the 10 is very least number. So the ECU 2 will transmit first and then ECU 3. The 12 will go out. Finally, the 98 will go out. So don't think that we have a list of messages here. The least one means in ECU 3, the 12 will jump to the front line and it will go out. No, not like that. Though it is the least number, where it is? It is the third level of the queue. Whoever is there in the top of the queue, he only can go in the bus when the bus is free. As per this logic, in the ECU 1, 30 is at the top, ECU 2, 225 at the top, and then 67 at the top. Arbitration will happen between these 3 messages first, and then once they are transmitted, then the next batch will come. Do you understand the concept of arbitration now to some extent? How that works, how the CAN does an arbitration and other stuff?
Yes. Yeah, I have one question here.
Please.
So whatever queue you mentioned, some data IDs over there in the form of X. These are the like CAN IDs or data?
Thanks. Actually, these are CAN IDs, not data. Data you can have that is 64 bits. You can have anything. The data bits are not involved in arbitration. Only the ID. Every packet used to have a unique number. Only that unique number is involved in the arbitration process.
Okay, understood.
These are the packet identifier. Every packet that we have that will have a number. That numbers are involved in the arbitration.
Is there any chances that the ID should be the same, like actually 30, 30?
I believe this is very famous question that I used to get in every batch that I used to start. Actually, that is not happen. That is not practical. If that happens, there is a problem. The ECU 1 and ECU 2 cannot have same identifier like 67, ECU 3 also transmitting 67, ECU 2 also transmitting 67. Is that possible? Answer is no, because every CAN packet in a network is unique. There cannot be duplicate. But is it possible for me to create a duplicate? Yes, it is possible. Using a CAPL, you can write, you can try those sort of idea. Practically, in real time, no, that is, two issues cannot have same identifier at the same time. That we have to understand. Is it clear or not?
Yeah, okay.
So during arbitration, always whatever the ID, for example, usually if you have 3 nodes at a time, arbitration will happen between 3 messages. If you have 4 nodes, arbitration will happen between 4 messages. If you have 5 nodes, arbitration will happen between 5 messages. That is how many number of nodes you have. According to that, you will have the messages involved, that is the identifier involved in the arbitration also will increase or decrease. If you have less node, only 2 nodes, only arbitration will happen between these 2. That is the thing that you have to understand. The thing is, there cannot be duplicate IDs. 2 issues cannot transmit same IDs. So every ID that we have in the CAN bus should be unique. Theoretically or in simulation, you create like that. If that happens, that is both the node will fail. Both of them will not go to the bus. You will get a bus collision. You will get an error frame. You will not see the 67 in the bus at all. Why? Both of them will try to go out. That will end up with the error frame. Any other doubts? No doubt. Shall we move forward? Yeah.
Yeah, okay.
CSMA means providing the equal opportunity when the bus is free to the everyone. That is what CSMA. When you provide like that, we have another problem. That problem is avoided using the arbitration. Multi-master broadcasting concept. That's what I already told about this. Whenever a node want to communicate to another node, it won't say, hey, a particular node, hey Ramu, you take this. Not like that. It will put the packet, but Ram knows that he need it. So he will take it and use it. When the packet is available in the bus, every node in the bus know about that. They know like some packet has come to the bus. Based on the ID, whether that is needed or not, they will decide. If needed for them, they will take it and process it. Otherwise, they will simply ignore it. Every node used to have a filter mask. They used to call as a mask register. Based on that, mask will be applied over the identifier which is coming in. If that particular packet, it is passed in the mask, then it will enter into the node and the node will take it and process it. If it fails in the masking, that will be ignored. That packet will not be taken into account. Another advantage that we have, I have listed out different advantages. First, CAN is serial. Second, the CAN is asynchronous. Third, CAN is democratic, otherwise CSMA bar CD we have in that. Also, CAN is differential, and CAN is having very great sophisticated error handling and detection and handling system. One thing is like, you don't need to write any separate program in CAN devices to detect the error. You also no need to write any program to handle the error. Both of them already VLSI logic, like using in chip itself, the error detection and handling is done. So you no need to write a separate program for it. It is implemented in the hardware itself to detect the error and to flag the error and then to handle the error. Everything already, the logic is available. It will take care. Again, that error detection mechanism is very sophisticated. Because of that, we won't get any loss in the information. When we exchange via CAN, it is very rare to get error. That's why they call that as a sophisticated error detection and handling system. The design goal. The CAN was introduced in automobile to make it reliable, safer, and fuel efficient. How that happens? When we exchange the information in between ECUs, they are able to make the judgment because they are getting the exact input that they want to make the judgment. Based on that, they can perform well. Today, the world is more connected. So similar to that, the ECUs are so connected in the vehicle. So they are able to exchange. For example, the driver information module, powertrain module can exchange engine status and other stuff with the driver information module so that it can display that to the driver as text messages or warning or telltale. We are able to perform well when the ECUs are exchanging information. That's why they come up with CAN. In the CAN, very standard, otherwise very famous one is version 2.0. It was made in 1991. When I was working in the industry, mostly I worked with version 2.0 only. I worked in the industry from 2007 to 2015. Till that time, most of the issues that I worked with are based on version 2.0. In 2012, BOS has come up with a modified CAN standard called CAN Flexible Data Rate. What is the advantage? The difference between 2.0 and FD is very simple. In FD, you can transmit up to 64 byte in a packet, whereas in case of version 2.0 or standard CAN, you can go up to 64 bits. That means only 8 bytes. 8 byte is possible, but in FD, you can go up to 64. As you have 64 bytes, totally it goes up to 4096 bits. You will get a delay. In single frame itself, 4096 bits. That will consume the clock cycles. Like communication speed will be very slow. To avoid that, what they are doing it, they have a different baud rate. When they transmit the control information, they will run it in normal speed. When they are exchanging the data, they will do that with high speed. That's why they call that as a flexible data rate. Whenever you work with CAN FD device, you have to configure two baud rates. One baud rate will be used for control information transmission, another baud rate used for data transmission. That switching will happen automatically. You no need to go or you no need to write any program. Only thing is in the beginning of configuration, like before energizing the device, they have to configure two different baud rates. When you analyze that with Keno, usually in Keno we used to fix one baud rate, whereas in case of FD you have to give 2 baud rates. That is the difference. Are you able to get some basic difference between FD and the CAN 2.0? Can you highlight some difference between these two?
Yeah, CAN and CAN FD, the major difference is 64-bit CAN FD has, and only 8 bits has CAN network.
Okay, in FD we have 64 bytes. In CAN standard, 8 bytes. That is major difference. As we have more data, the FD will use 2 baud rates. When they are transmitting the start of frame and the DLC, these are control bits. When they transmit control bits, they will go with the slow baud rate. When they are transmitting the data, they will increase the baud rate. That means speed at which they are transmitting, that will increase. But this will happen automatically. We no need to write any program for that. That is the major difference that we have between the 2.0 and FD. This is theoretical difference. I will explain you how that works and in later point of time. The next thing is the FD and 2.0 can exist in same bus. You can have some nodes which is working with FD, some issues which is only support 2.0. Both of them can coexist in the bus. Only thing is their baud rate should be same. If that is same, it will work. It is an European method, otherwise European culture to standardize everything. You have to eat like that, you have to dress like that, similar to that. Because something becomes popular, they will standardize that. They standardize and see. Now, similar to that, when the CAN become popular, they ask the boss to write a specification. Every automaker should follow that standard. That will be released as an ISO document. So it has a number 11898. Every document used to have a number. The CAN also has a number 11898. It's explain about how you have to do the CAN communication. Today, the CAN has widespread use. You can find CAN everywhere. Not only in automotive, the industrial automation, agricultural, robotics, everywhere you can find the CAN. The CAN can be employed when you want to process automation. So something like when you want to exchange information between 2 different electronic devices, the CAN is more appropriate. Even in avionics, in flights communication, right? Different issues in the flight can communicate via CAN. That is also possible. The CAN standard has 2 layers. 2 layers are implemented in hardware itself. OSI model used to have 7 layers. Among those 7 layers, only 2 layers are available in hardware, in the chip. CAN is a peripheral in a microcontroller. In CAN peripheral, only 2 layers are implemented. Usually I am seeing many videos in the YouTube. The people used to say, people are saying like all 7 layers are implemented in CAN. That is wrong. Only 2 layers are implemented in the OSI model. Only the 2 layers of that model is implemented in the CAN in hardware. For the rest of the things, it doesn't mean that you cannot use them. For them, you have to write programs. You have to write microcontroller program to handle the rest of the layer. But these 2 layers, you don't need to do anything. It is already programmed in the VHDL or Verilog. It will just work. You have to configure it. That's all. That layer will work. It will do their job. This data link layer, it has a different rules how that data link layer exchange the information. They have different methods like message type, arbitration rule for bus access, fault detection mechanism. All those things are coming under data link layer only. Whenever you go for interview, if interviewer asks like how many layers are implemented in CAN, don't say 7. All 7 is not implemented. Only 2 layers, physical and data link. Only 2 layers are implemented in CAN peripheral. Again, why we have to go for CAN? The CAN is a measured standard. It has been in the market nearly 42 years. In 1980, it was started. Even today, the CAN has its own room. In modern automakers are moving towards something called automotive Ethernet. Why they go for that? Because today people want to exchange huge number of data. They want to exchange videos, they want to exchange big files, messages. They want to have a higher bandwidth. The CAN, you can go up to only 1 Mbps is the maximum. You cannot go beyond that. You cannot do a communication using CAN more than 1 Mbps. That's why they go for automotive Ethernet. The Ethernet is there from the moment they find out the communication, the computer networks. From that day onwards, we have Ethernet. But automotive Ethernet is somehow they modified that stack and then they made it to suit for automotive industry. That is the difference. Other than that, from olden days, a lot of libraries have been written for TCP/IP communication. Otherwise, the Ethernet communication. Those things you can easily bring to the automotive industry when you follow the automotive Ethernet. But though they have a lot of challenges to do that communication, the people want that because today people want to exchange big videos, big documents, very huge data. Those are not possible via CAN because CAN has a limitation. It can do the exchange of information up to the rate of 1 Mbps. When you see any CAN ECUs, those who have industry experience, they know about it. You can see up to maximum 500 kbps. Like you can find 500 kbps, 250 kbps, 125 kbps, but not above 500 kbps. That is because they use the 50% of the communication speed as a buffer. So they use only 50% of capacity of CAN. So they don't overload it. They don't completely utilize the 1 Mbps is not used, but you can go up to 1 Mbps. As the CAN is used in a commercial vehicle and then people are, because they are going to deal with human lives, they go up to 500 kbps as a maximum speed. You will find every ECUs which is equal to or less than 500 kbps. You cannot see beyond that, though we can do it up to 1 Mbps. That is the reason that you have to know about the CAN. The speed of CAN is maximum 1 Mbps. CAN is cost effective. Actually, I won't agree with this one because the CAN is a little bit pricey. If the CAN is cost effective, we have another standard called LIN. Do you people know about LIN? Local Interconnect Network. Most of you know, right? LIN communication standard. LIN is similar to CAN. But the LIN was invented after the CAN. You assume the LIN also a serial communication standard. and then it can be used to exchanging information between ECUs. It is having only one wire. There is no differential voltage in terms of LIN. We have many things. It follows the master and slave concept. So there are many things are there. But do you know one bitter truth about a LIN? The LIN was found because the CAN was pricey at that time for automakers to implement in their car. Because the CAN need, maybe the chip level, the cost might be peripheral wise, it's very simple. But when you make that as a product, you need a respective analysis tool. And then when something goes wrong, you are able to know how to troubleshoot it. The automakers felt that as an expensive one. That's why they devised, after we have CAN, the people have created a low cost version. It is something similar to, we used to have some branded mobile like Apple mobile. Those who are unable to afford that mobile, they can buy some Chinese mobile. It's low cost, which used to have all the features that we are finding in the branded one. But only thing is, it will heat very quickly. It will crash very often. Sometimes it will break. It will not work after some time. We have those issues. So similar to that, but Chinese version is made based on branded version. They simply made a copy of that. So similar to that, the LIN is somehow a low cost version of CAN. Because in those days, when the CAN was famous, the people were unable to implement that in their product. They want a low cost version. That's why the LIN was invented. I would agree about cost effective. When you compare the cost of implementing CAN within other communication standard that we have in the market, when you compare the CAN with the rest of the thing, the CAN is cost effective. That's why they say that as a cost effective. But usually when you compare that with LIN, the CAN is somehow pricey. Simple transmission medium. In order to perform a CAN communication, if you have twisted pair of wire, that is enough. You can even go for fiber optic cable, radio wireless link. You can do the information exchange, even using those physical medium, physical or wireless medium. It is not only that you have to use only twisted pair. The CAN has excellent error handling. The CAN uses CRC, error reduction mechanism. It is a very easiest one and it's more straightforward in case of CAN. That has been used to find out the errors in the packets. In order to understand CRC, I used to give a layman example for every student. Like, I am writing a letter to my friend. At the end of the letter, I count all A in my letter and then I put the number of A's in that letter. After writing it, I am finding some 50 A's in that, just to mark 50 at the end of my letter. Now I am sending that letter to my friend using some olden days, the people used to send it via pigeon, different mechanisms, not like email. The moment my friend received that letter, he will, before reading it, what he used to do is he will count number of A's in the letter. Myself and my friend know about that. I have encoded the number of A's as an authenticity of the letter. If the letter has exact A's that was encoded at the end, my friend will consider that as an authentic letter from my side. If it is not matching, he will simply reject. This letter is biased. It is modified. That mechanism is used in the CAN. Based on the data bits and control bits that we have in a packet, they will come up with a 2-byte number. That number is attached with the every packet that they are trying. For every packet, it is calculated and attached at the end. As like I am counting number of A's and marking at the end, they find out a 2-byte number based on some CRC calculation algorithm, encode the 2-byte number at end of the packet. The moment the receiver receives packet bits one after another, because it is serial, at one point of time, it will reach the CRC. The moment it reaches the CRC bits, the receiver will have its own calculated CRC. I will explain you how that works. It used to compare the calculated CRC by the receiver with the received CRC. If both of them are equal, it will consider that as a valid packet. Otherwise, it will simply ignore that packet. Let me explain you how that works in CAN standard. When you go and attach a CRO in the CAN physical line, see this is CAN high line and CAN low line. See here, there is a complement of the signals. Now you know why they made a complement. The reason is to avoid the noise. The above one is the bits of a CAN packet that I have to transmit. How they will do? From the start of frame till end of your data frame, whatever bits that you have, they are used to calculate this number. Initially, the transmitter has start of frame and then ID and DLC, entire data frame, all those things it has. Using these bits from start of frame to end of the data bits, it come up with a 2-byte number that is encoded, that is attached at the end of the data bits. This train of pulses, train of bits is moving toward receiver via shift register. They used to shift them using the shifter, which will produce a voltage fluctuation. 0 will go like 1 voltage, and this is the voltage which is going from transmitter to receiver. So as they are going serially, the moment it receives the first byte, the receiver, it used to calculate the CRC for that one. Every bit which is coming into the receiver will be put into the CRC algorithm, and at the moment, because it's serial, so it shifts second byte, third byte, fourth byte, like that. At one point of time, it will reach, the transmitter will try to shift the CRC first bit. At that time, the receiver has received all these bytes serially. It has calculated the CRC is ready at this point. What it used to do, the receiver will compare its calculated CRC with this CRC bits, those are shifted from the transmitter. Both of them are same, it will accept that way. If they are different, it will simply say this packet is an error on its one, and it will simply reject. So in that way it works. Do you understand how the CRC mechanism is used to find out the errors? Is it clear, or you have doubts? If you don't understand, please ask me. I am ready to explain one more time.
In the CRC field, 2 bytes of CRC you're sending, right, to the receiver. Do you have any standard signals you have to send to the receiver, or how the CRC will be calculated?
As per CAN standard, there is a algorithm. There is an algorithm to calculate CRC. The CRC is calculated using the bits from the start of frame up to the last data bits. From this bit to this, I believe you are seeing my mouse movement. So from this bit to this bit.
Okay.
Whatever the bits that you have, right, in between, all of them are sent to the algorithm. I will explain you. There is CRC calculation algorithm. That algorithm will use these bits and come up with 2-byte number. That number only encoded here. There is an algorithm available that is explained in the CAN standard.
Okay.
So let me ask this question, because this is to confine that you understand the logic. Could you explain how the receiver is calculating the CRC?
The transmitter will calculate from start of frame to this data field.
Okay, end of the data bits.
End
It
of
is
the
calculating.
data field, yeah, up to the red one. And then receiver will calculate the from start of frame to end of the data field up to the red one.
Oh, how it is? Transmitter, because these data bits are in the transmitter side, so it is calculating and attach it at the end of data field. How the receiver knows about it? So these bits are, I believe you people are seeing my mouse movement. These are the bits that we have in the transmitter side, right? As it is a serial communication, these bits will go one after another. First time the 0 will go from transmitter to receiver. Receiver will get the 0 and will send that to the CRC algorithm. The 2 bytes of CRC byte in the receiver will modify it. Then it receives another 0. It will send that to algorithm. Then another 0. Not 0, another bit second. It will send every bit that it receives from the transmitter to the CRC algorithm. How long? Till it reaches the first bit of the CRC field from the transmitter. The moment it comes to know that this is the first bit of CRC from the transmitter, it will stop calculating the CRC. Then it will go to the compare mode. Because the moment it sees the first CRC bit in the receiver end, the receiver will conclude that, alas, our job is over. Now we have to compare what we calculated with the what we are receiving. So it will simply compare XOR or something like that. So it used to compare the incoming CRC bits from the transmitter with the its calculated.
Sir, how system knows that is the CRC first bit?
Earlier, super. The thing is, they know the frame structure with respect to the control bits. First bit is the starter frame, they know that. And the next 11 bits are identifier, they know that. RTR bits, next one is an RTR bit, then IDE bit. All these things they know. And then next 4 bits are DLC bit. Based on this DLC, when you see this DLC, they have only 1 byte. They have encoded only 1, 0001. The moment they see that as 1, they will only go up to 8 bits, because 1 byte is equal to 8 bits. After 8 bits, they will say, okay, the data bits are over. After data bits, the next bit that we are receiving is CRC. They will make the conclusion like that. See, this up to start frame to DLC, they are fixed bits. They know the fixed slot. So this is the start frame, and then this is the IDE first arbitration, that is the IDE first bit, second bit. They know that because they are fixed size. When it comes to DLC, the DLC has flexible size. Sometimes it used to have 8, sometimes 1. Maximum you can encode up to 8 in case of DLC. So they know that after seeing the DLC, the next here they encoded 1. When they see 1 here, they will take next 8 bits as data bits. After the 8 data bits, obviously they know that the next bit is CRC. All these things, see how systematically it works. Initially, the starter frame is coming. Next, the IDE fields are coming. These are IDE fields that receiver know that. Before coming to the data, they are sending the DLC. They are not sending data first and then DLC. The receiver will know that this is what the total data size is, and this is what the data is before it receives the data. See, it knows the size of the data before it receives. After that, obviously, it will come to the conclusion that, okay, the next bit is a CRC. Like that, they make the decision. They placed the control field more appropriately to make the right decision at the right time.
What is the IDE bit, sir?
We are going to study that in separate slide. Explaining it now will make some confusions. This is how the CRC is working. Fault confinement. The CAN has built-in fault confinement. That means handling of errors. It has active error mechanism, passive error mechanism, burst off mechanism. I will explain them in detail what they are and what for they are used when the right time comes. As of now, you understand that CAN has very good fault confinement mechanism. That is enough. Most used protocol in industrial and automotive world, the CAN has been used, that is extensively in automotive industry.